Okay, we're recording. Great. So today what we're looking at is we're going to start looking at searching algorithms, and we're going to introduce the first of those, which is linear search. And then next week we will go through the second of those, which is the more complicated one called binary search. So when we talk about searching algorithms, what we're talking about is a set of step-by-step instructions that a computer uses to find a specific piece of information within a larger collection of data. So we may have this massive collection of data stored in an array or stored in some sort of data structure, and we need an algorithm to find a particular file or to find a particular value. So we need a way of searching and traversing that larger data structure in order to find that specific piece of information. So what we often refer to is a target item. So a target is what we're looking for, and that is what we're trying to find in any given data structure. So it could be a number in a list, a name in a database, or a file in a hard drive. No matter what we're looking for, it's still just the idea of trying to find a specific target. Now, searching algorithms are very, very important in computer science because so much of what we do in technology involves finding information. So every time you search for a video on YouTube, so think about when you go to YouTube and you search something up, that is a searching algorithm that's being applied at that time. When you look up a contact on your phone, that's a searching algorithm that's trying to find a particular contact. When you search for a song on Spotify, when you use a search engine like Google, when we were just looking, remember we were searching on your laptop for Google Drive, the application? That was a searching algorithm that was looking for that.
Didn't we talk about this at TC?
We touched on it, correct. Yeah.
The Spotify thing?
Yes, yeah.
Okay.
So Spotify is a massive database full of songs. When we search for a song, there is a searching algorithm that is applied to go through all the data.
2D array?
Well, it depends on how the data structure is stored. So we're going to keep it simple and just look at a 1D array, but if it's in a 2D array, then there may be a particular algorithm to go through each row and each column. Yeah. So we did look at this last week when we looked at traversing data structures. This is a way of traversing a data structure. The first one we look at today will traverse the data structure. The second one we look at next week does not involve traversing it. It's a more advanced algorithm. So the key reason we study different types of searching algorithms is for efficiency. So as our data collections grow to be incredibly enormous, think about the amount of songs that are in Spotify. Okay, as those data collections get to be enormous, think about Google, the amount of websites on the internet.
Millions and billions, and it's so big that it would take more time.
Correct.
Time complexity would be like ON.
Yeah, well, depending on which algorithm. So we're going to look at two.
Linear.
Yes, is ON. So the first one we're going to look at today is linear. The one we'll look at next week is binary.
Would that be the one?
We'll look at it next week. Okay, so the difference between a fast algorithm and a slow algorithm can mean the difference between a program that works instantly and one program that is unusably slow to use. Okay, so the choice of algorithm here is very important. Okay, the first method, or the first algorithm for search that we'll be looking at is called linear search, also known as sequential search. So this is the simplest and most straightforward search algorithm. This algorithm is super simple. It basically sequentially checks each element in a collection until it finds a match, it finds that target value. Or if it doesn't find the target value, then it reaches the end of the collection.
Then we get an error?
Not an error, but we will have some sort of thing in our code to say could not find. Correct, yeah. So if you look for a song that is not on Spotify, it's not going to crash your program. It will just be like, that song's not here, if that makes sense.
Oh, so that's like when I look for maybe a song on Spotify and there's no, it doesn't exist yet. It will say we couldn't find the song, error message.
Yeah, but notice that it didn't crash your computer. So it would have gone through. It wouldn't use linear search, by the way, on Spotify. It would use more advanced searching techniques, but hypothetically, it would go through every single song in the Spotify database and looking for a song that's not on Spotify. So it would have gone through every single song, and then if it didn't find the song, it would have got to the end and say, song does not exist on Spotify.
So is it similar to like maybe like a while true? Or like a try and accept?
It uses a for loop. Typically
loop.
uses a for loop.
I was thinking maybe like so like.
I mean, you could do it with a while loop.
True.
Yeah.
Yeah, and then like error, it would put like a message like could not find a song, but if false, I guess.
Yeah. So if there's no match, if target not found, then cannot
If
find.
we not found, then print could not find the song.
Yeah, great. So you can see here, we're trying to find the value 20. We start at the start of the data structure, the array. We look first to the first index. It's not there. We go to the next one. It's not there. We go to the next one. We go to the next one. We go to the next one until eventually we get to index 6 and we find 20 and we return that value. So here's how it works. We start at the first element of the list. We compare the current element in that particular value. So we're comparing this one here to the target, and we're checking to see if they match. If they match, the search is successful and the index of the element is returned. So hypothetically, if we were looking for 10, we would have found 10 and returned 0. We'd return the...
So if we find 20, it returns 6.
Correct. It returns the index of the element that's found. Now, if the search is not successful, if they don't match, we move to the next element and repeat the same step, the same comparison. So check to see if the value in index 1 matches with 20. It doesn't, so we go to the next one, so on and so forth. If the end of the list is reached without finding a match, we conclude the search unsuccessfully and we can say that the target item is not in the list. Okay, so you can see here how it works. We check for 10, so we're looking for 45 in this example. We check 10, it doesn't match the target, we move to the next one. Check index 1, that's 25, that doesn't match, we move to the next. Check index 2, doesn't match, go to the next one. Check index 4, index 3, it does match.
So it doesn't move to the next.
It doesn't even search these two. Yeah.
So because it already knows that
45 is in this. Correct. So this will return index 3. Yeah.
So if it doesn't find the value you're looking for, does it just not return anything?
It returns, if it doesn't return the value, I'm pretty sure it returns -1, and I'll talk about that more shortly. So let's have a look at the time complexity of this first before we look at some code. So the time complexity, the best case. So remember, what one do we focus on? Which do we focus on? Yeah, we focus on big O, but it is kind of interesting to look at the other two. The best case scenario is actually constant time. Why do you think it's constant time?
Because if the element that we're looking for is the exact first item in the list, it will not take.
Yeah, it doesn't need to.
You need time to look for it. It just does it and boom, you're done.
Great, excellent. So hypothetically, if we were looking for 10 in this example here, this would be constant time because we look at the first one. Oh, it's the first element. We return that. That is a constant time operation. Okay. But how often are we going to get a list where the first item is always going to be what we're looking for? Not often. So again, that's another good reason for why the best case scenario is not
useful.
Correct. Yeah. The average case, on average, the algorithm will have to look at approximately half of the elements, which would be n divided by 2.
Log n?
Not log n. It would be n. So if each time it had to go halfway through the list, it would be n over 2.
Oh, okay.
And remember, we removed the multiples and we moved the division, so this would be the big theta of n as well. So this grows in proportion to n because it would have to go through half of the array on average. Of course, worst case, what's the worst case scenario for this one?
Is that if the target element, like for example, the 45 is the very last item?
Yep. Or what's also the worst case?
Or doesn't exist?
Yeah, great. Because if it's not there, it still has to check the whole data structure, which is n time.
N times.
To-
And then it goes to the end of the list and just doesn't return anything.
Correct. So the worst case is O of n. All right. So generally speaking, if we look at the advantages and disadvantages of linear search, it is a very simple algorithm to understand and write. We'll have a look at the code shortly. So it's one of the most straightforward search algorithms to understand and write. The logic is simple. Check each item one by one. It works on unsorted data. So some other algorithms that we're going to look at, like binary search next lesson, that requires the data to be sorted beforehand. Linear doesn't require the data to be sorted beforehand. So any lists that are unsorted or may take too long to actually sort, then we could use linear search. Yeah. It's very memory efficient. It doesn't require any additional memory to run. It just goes over the existing data structure. It doesn't need to create any additional memory. It just iterates over the data structure. So it's very memory efficient. And it's generally good for very small data sets. So if we had a small data set, because we know it's not good for big data sets because it's O to the n, but for a small data set.
So the disadvantages would be it's bad for bigger data sets.
Correct.
And that it runs on worst case.
Yes.
performance.
Yeah.
But
So
has a bad worst case, which is ON.
yes, that's right. So it's good for small data sets, but for very large data sets, it's very slow because its time complexity is O of n, meaning the search time grows in proportion to the number of items in the list. If we were searching for an item in a list of 1 million items, that would take, in the worst case, 1 million steps to process it, which is quite inefficient. And the worst case performance is when the target is at the very end or not. And as we said, they need to go through every element. So those are some of the disadvantages of linear search. We might look at some code now of how linear search works. So I've got a program here called linear search, and we can see here. Yep.
For value in data.
Yep. So for each value in the data.
Value in the data.
Yep.
And if value that we want is equal to a target,
Yep.
then it returns the index.
Yep.
Oh.
And if it doesn't,
The negative one.
yeah. So this, remember how I said before. So so this will go through each data in the data set. I mean, here we've got some sample data that we can use. So it's going to go through every one of these one by one. So for each value in data, it's going to check to see if the value matches with the target. If it doesn't match, so if it does match, it'll return the index for that particular item. So
If it's not found, it will increment by 1.
correct. It's going to increment by 1 and then check the next index.
And if it doesn't find it at all, it returns -1.
Correct. So if it doesn't refine it at all, the target was not in the list, and it returns -1, and this is a widely used convention to signal that the search was unsuccessful. The reason why -1 is often used is because it can't be confused with O or 1 or 2 or 3, because as we know, 0 is an actual index element. 1, 2, 3, 4, 5, 6 are all index
There's
elements.
no such thing as a negative index.
Correct. There's no such thing as a negative index. So we can return -1 in this
So why
situation.
doesn't it return like null or NA?
Null is sometimes confused with 0. So in some programming languages, 0 and null can sometimes be.
Like C?
I'm not sure about C. It's maybe some older ones. 0 and null were kind of used similarly, and to avoid that confusion.
Well, NA?
I mean, you could just say no data, okay, but the common
But like, mostly it's just -1.
the common convention is to return -1. Yeah. So we can have a look at this data here, and if I run this particular, let's have a look at it. So what do you think I'm doing here with this? So that's my data.
That's the data.
Yep. What do you think this should return?
It should return -1.
Yeah, let's give it a go. So Python 3, linear search, -1. Why did you say -1?
Because 2030 doesn't exist in the data.
Okay, good. Let's try 5. What do you think this will return? 3. Let's give it a go. 3, yeah. So 0, 1, 2, 3. Okay.
Is there a way we can make it like ask for user input first?
I mean,
Looks for it.
yeah, so you could say, we could say here, target equals input what number to find, and then we could convert that to an int. And then here, instead of searching for 5, we just say target. So here, what
Yeah.
number?
9.
9? 5. If we try 3,
2. Wait, 1.
1. Yeah.
Try like 100.
100 minus 1.
Okay.
So this is an example of a linear search algorithm. What do you notice about the code? It's very simple. It's
So
a
if
very
we add more elements into the data list,
Yep.
it would take longer.
yeah. So if I added 33 and 45 and 99 to search for 100 now, it's going to have to go through n elements to search for 100.
But I think it's only in milliseconds, so it's minutes.
What's that?
Like, I think the time will still return like in milliseconds.
It'll still be very quick.
Yeah.
But remember, when we talk about big O, we're talking about billions and millions of summers.
So
Okay.
like, if we're scaling like millions, and it'll take much longer.
Yeah.
Like a 30-minute or 30-day example.
Yeah. It would take a long, long time. Yeah. All right. So that's linear search. Next lesson, we'll start to look at a much more efficient one called binary search.